know why I left such a big, beautiful space. But you don't have this space, but if you did, you could put a happy face there. Position vector of a point with respect to a fixed origin is the vector OP. So most of the time we deal with vectors that can float all over the place. So when we say a vector is an x value of 3, a y value of 2, 1, 2, 3 over 2 up, that would be this vector, and it could be anywhere. But if we want to fix it in place, we often start with the origin and say, if I'm starting at 0, 0, and going to the point 3, 2, now I have a fixed vector exactly in that spot, starting at the origin and going to a specific point. So this is no longer a free vector, and our position vector, and we can practice putting the arrows over top of those bold letters, is OP. So we have two position vectors here, position vector M and position vector N. And the question is if you were at M and you wanted to get to N, but you had a robot that could only move in these two directions. It could move in this direction M and this direction N. Could you get there? Right? This is very, technology has advanced. Usually robots can turn in any direction, but let's just say that this robot can only travel in the direction of M and in the direction of N. So if you wanted to get from M to N, could you see that you could say, hey, why don't you go backwards along this way, get back to the origin, turn around, and then go this way, and you would get from M to N. And that would be only going along those paths. So how would we write that? Well, we would write that as saying, first I went backwards on M, I got back to O, and then I went from O to N. Look at this. This would be M-O, this would be, look at that. And this is going to be sort of the idea. We're going to have certain position vectors, and then we can talk about going anywhere, but just restricted to just using those vectors that we had to begin with. Okay? If you wanted to go from N to M, all right, so going back to this diagram, now if I wanted to go from N to M, can you see that you could go minus N and then plus N? So you're going to find that I am going to write it this way a lot. You will see a lot of textbooks write it this way because people think that looks nicer not to start with the negative. Okay? It means the same thing, but I find when you're trying to understand it and you're thinking about the diagram, isn't it easier to think about first going backwards on N and then traveling on N? It is. Okay, I'm going to draw M in blue here nicely, and I'm going to draw negative N in green. And I'm going to show you that if you did M first, so we're at N, and I did M first, that's where you would end up. And then if you subtracted m, you would still end up at m. But it doesn't fit in your diagram to follow paths easily for your eyes. Okay? So when you ever want to find any vector between two things, you can use their position vectors, subtract one to get back to the origin, then go from the origin to the point you want to go, is a logical way to do it. Okay? But a lot of textbooks will write it like this, m minus n, just because it looks nicer for the math. It's up to you. Okay? I like this better for how it makes sense. So now, oops, we've got a point P right here in the middle, and you want to go from here to here. But again, your robot only travels along M and N. So, I want to go from O to P. What could I do? I could go, right, if I imagine myself going along here, what can I do? Well, obviously, I could travel from O to M. That's no problem. If I can get to P, then I'd be fine. I've already figured out M to N. I can already travel in that direction from M to N. I figured that out as well. Does it make sense that if P is the midpoint, all I would have to do is travel halfway from M to N? So what I do as a starting point is I figure out, okay, I could go from O to M, and then I could go halfway from M to N, because that would get me to P. Now with that in mind, in terms of these arrowheads, M and N, O to M is M plus, and we already figured out that M to N was negative M plus N. So we can distribute this half, just like we would do with regular numbers, and combine like terms, and we will get half of M plus half of N. Now what's really cool about this, we wanted to get to the midpoint P right here. We figure out the midpoint of M right there. We figure out the midpoint of N right there. I draw this halfway. I draw this halfway. And according to what we calculated, to get from O to P, we can go halfway to M plus halfway to N. Let's see if that works. If I go, here's the halfway to M, put that down, here's the halfway to N. If I add that on, and if I had drawn it perfectly to scale, it would be like amazing at this moment, where you'd be like, wow. But I think we get the idea of how it works. So now we have three position vectors, A, B, and C. P and Q are midpoints of A, B, and B, C. And so the question is, how could you get from O to P? How could you get from O to Q? So the position vectors. And so we start traveling. If I want to get from O to P, I could go from O to A, and then go halfway from A to B. O to A is just position vector A. How could I get from A to B? Can you see that you could get there by going backwards on A and then along B? If I went backwards along A, that would be negative A. And then forwards on B. And so from O to P is going to be equal to, if I combine my like terms, half of A plus half of B. And this would be position vector P. Position vector Q can be done the same way, right? If we think about going to Q, I could go from O to B, and then halfway from B to C. And that would let me write it as vector B plus half, and B to C would be negative B plus C. One half of B plus one half of C. So now we want to tell our robot, who can only travel in the directions of A, B, and C, that you want to start here at P and end at Q. And initially this looks like it would be really hard to do, right? Probably if I was, if you had levers that could make it go forward and backwards, you had an A lever, a B lever, and a C lever, probably I would make this robot go like this. Right, and it would do some sort of jerky line like this all the way along, and I'd be like, can I get it there? And you'd be like wiggling the levers all the way along, okay? If we have our position vectors, right, now we have a position vector for P, so we could go back to O, and then go from O to Q. We could say that PQ would equal back to the origin on P plus from the origin to Q. And those things we found last time, now we can write them as negative, this is 1/2 A plus 1/2 B, plus Q, which is 1/2 B plus 1/2 C. And if we simplify this, we're going to get 1/2 C minus 1/2 A. Which seems really simple, right? There I am moving all my levers like crazy, trying to jiggle it all the way to get there. And somebody else just goes, if I take halfway to C, and I take a negative halfway to A, if I started on P and went halfway to C, and then went back halfway to A, it gets me perfectly to Q. So the idea of vectors is that we can simplify how we get from one place to another, especially if you have restrictions like this, that things can only travel in certain directions. But it's, I don't know, that moving those arrows and having it line up nicely like that. And your logic, if you needed to go, if you had these levers that were on a remote, your logic wouldn't tell you, oh, I'll just go like this, and then I'll turn this way, and it'll work out fine. So I'd like you to try writing out these three on your own. All right, did you get A plus B to go from O to D? And then to go from B to D, could go minus 2 A's minus a B. So visualizing that. Minus A1s. Where are we starting? Oops. Starting from B and going to D. Minus A twice and then minus B once. And then finally, from C to F would be minus 2 B's. So interesting here, you don't have to go, once you realize that this length is equal to that length, because it's a hexagon, yes, you could go from C to F by taking this long way around, and that would work, and once you simplified it, you will get just minus 2 B's. But because vectors are free, you can just say, oh, well, if I know B is that way, I can just recreate it here and go twice in that direction for B and get from C to F. So this is sort of the idea of a vector being free and floating, like your robot that you're controlling with the remote control. If you have a command that says, go this way, this far, if you move your robot over here, it's like it'll still go that way, that far. It doesn't matter where you're starting from. Its command stays the same. All right, now we'll get into same idea, but add some ratios. So here we have a parallelogram. Because it's a parallelogram, okay? Some things about parallelograms, they're called parallelograms because the opposite sides are parallel. And because the opposite sides are parallel on both sides, they also have to be the same length. So going from O to C is the same as going from A to B. And here we've got a couple of points. We extended a point P so that the ratio from A to B to B to P is 2 to 1. So that means that if this length is 2, this length is 1. It could be that this length is actually measured to be 10, then this length, actual measurement, would be 5. It's in that ratio. We know that A to B is double the length from B to P. And same thing, CQ to QB, the ratio is 1 to 3. So if CQ is 10, then Q to B would be 30. And any numbers in that ratio. So with that in mind, we've only got those two directions, A and B. Can we get anywhere on this diagram? Can we get from A to B? Obviously. I would go backwards to the origin by going -8, and then I would add B. Now, if I wanted to go from A to P, how do I use that ratio to do that? Okay? does it make sense to you that A to P is longer than going from A to B? That should be obvious. So, but it's not double the length. I can't just go 2 times A to B. I would have to go, if you do it all in one step, does it make sense that you could go 3 halves A to B? Okay, so that's all in one step. If you don't like for some people, there's like that 3 halves is hard on their brain. For some people, they like going from A to B and then going half of A to B again. Does that work better in your brain? So, definitely. I'm the second way too. For my brain, like what makes me happier is the second one. That I'm going from A to B and then going halfway again. That makes more sense to me than rewriting it as the ratio 3 halves. But what's 1 plus a half? It's 1.5. It's the same thing. So either way that you do it, what we're going to have is 3 halves of negative A plus B. So that will equal 3 halves B minus 3 halves A. And now if I want to start at O and get to P, well, I could go from O to A first, and then from A to P. I've already done A to P, so O to A is just A plus, this is 3 halves B minus 3 halves A. So give me 3 halves B minus half of A. And again, because I have a smart board and it's so much fun to play on it, I'm going to look at taking a half of B, which is about there, and I'm going to take a negative half of A, which is about there. So if I started at O and went from O to B, then O to B again, then O to B again, and then subtracted half A, it worked out perfect. It's, I guess, harder than it looks to estimate exactly where halfway is. I knew I was short at this point when I was like, oh, I didn't even get to B with 2 halves. This is going to be a little bit problematic. And now we want to get from O to Q. So I could get to O to Q by going from O to C, and then going from C to Q. So O to Q definitely would be O to C plus C to Q. And now we're going to do some interesting math. Are you okay if I replace O to C with A to B? And if I replace C to Q with just 1/4 of A? So this is the abstract step. It's a little bit abstract because you have to go from parallelograms. I know that O to C is the same as A to B. And I know that C to B is the same as O to A. So C to Q, which is 1/4, does that fraction make sense to you, that that whole length from C to B is 4? And so C to Q is only 1/4 of the way. And that 1/4 of the way is just 1/4 of the way along A. I've already figured out that A to B is negative A plus B plus 1/4 A. And so my final answer will just be B minus 3/4 of A. And in the final question, you're at Q, you want to get to P. Ooh, it almost looks parallel. Maybe it is. Maybe it's not. Who knows? How would I do that? Well, if I want to go from Q to P, I could go back to the origin and go from the origin to P. And since I've already figured out both of these, this one's just going to be a negative of what we found before, which was O to Q was B minus 3/4 A. So I put a negative in front of that, and that would get me from Q to O. And O to P was 3/2 B minus 1/2 A. So putting this all together, we are going to have 3/4 of A minus 1/2 of A, which is 1/4 of A, and 3/2 of B minus 1B is 1/2 of B. Now you might want to show a little bit more work with common denominators when you're doing your work. It's fine, but it works out beautifully. Position vectors of 3 points. Now we're in 3 dimensions, which is hard to visualize. And we've got 3 points and are given their position vectors, and we want to show that A, B, and C happen to be on the same line. So let's just take this one level down to 2 dimensions. Okay? I can draw 2-dimensional grid, and I could easily put this point, and this point all on the x-axis, and you would tell that they're collinear, which means that they're on the same line, no problem. Okay? It would be a little bit harder if I told you 3 points like this. Would you agree? That if those 3 points are like that and we wanted to show that they're on the same line, there's a couple of things you could do in 2-dimensional math. You could figure out the distance from here to here and the distance from here to here. And if it was the same as the distance from there to there, would that make sense to you? Then they'd have to be on the straight line. Because if the red distance was shorter, then that would tell you your blue lines went off and weren't in a straight line. So one way that you could show that they're in a straight line in 2 dimensions is with distances. Another way that you could show that they're a straight line in 2 dimensions is by showing that the slopes are the same. If they're going in the same direction and they share a same point, they have to be in the same line. Now we're going to do that, but now we have 3-dimensional vectors. We've got vector A. So I'm going to, here's our position vector for A is 2, -1, 1. Our position vector for B is 3, 2, -1. And our position vector for C is 6, 11, and -7. So, option number 1. Let's go with distances, because we know how to find the lengths of a vector in 3 dimensions. What do we have here? We have, in 3 dimensions, some origin. We've got some point A, some point B, and some point C. And we've been told these position vectors, there's A, there's a position vector for B, and there's a position vector for C. If I want to go the distances route, I would need to figure out A to B, how long it is, B to C, how long it is, and A to C, and how long it is. So if I'm going to use a distance strategy, that's what I would do. How hard is it to figure out A to B? Well, if I wanted to go from A to B, that would just be going back to the origin plus B, or B minus A. Ooh, I should do that. No, it doesn't. Thought I was going to color code it nice. I've decided not to. If you do B minus A, you get 1, 3, -2. If I go from B to C, that would be -B plus C, 3, 9, and -6. And finally, A to C would be -A plus C, or C minus A. So you see that the C minus A, or the B minus A, or the C minus B is easier for mental math for figuring things out. So I wrote -A plus C, because that makes sense for me for how I get from A to C. But when I actually do the math, I'm going to go C minus A, 6 minus 2, that's 4. 11 minus -1, that's 12. And -7 minus 1, -8. Length of AB, square root of A squared plus B squared plus C squared. 1 plus 9 plus 4, 14. The length of BC, A squared plus B squared plus C squared. 9 plus 81 plus 36. Square root of 126. And A to C stretching my mathematical. 16 plus 144 plus 64, that's 160, 226. So when we're finding the length,
Oh, but we're just squaring it. Okay.
we're doing a squared plus b squared plus c squared.
Yeah, 24.
Hmm?
224.
Yes, 224. Thank you. There we go. Now, does this plus this equal this? How many 14s does it take? How many 14s? Do you know your 14 times table pretty good? There's 9 of them. So if this is 9 times 14, I could rewrite this as 3 root 14. And how many 14s in 124? 16 of them. Which is, square root of 16 is 4, so this becomes 4 root 14. The length of AB plus the length of BC is equal to 4 root 14, which equals so method 1, we could use distances. That would be the same thing you could use in 2 dimensions. We've extended it to 3 dimensions to say that these form a straight line. The other thing that we could use is slopes, which is actually going to be, I use the distances first because I think it's more intuitive that you would see that, but I think the math takes a little bit longer. Does it make sense that if AB and BC are parallel, then all 3 points are in a straight line? Does that make sense to you? Now in vectors, how do we show 2 things are parallel in vectors? They'd have to go in the same direction, but one could be longer than the other one. That would be okay. So my question is, for example, B to C equal to some constant times A to B? If it is, then we know that they're parallel. Now B to C is what? We figured out B to C was 3, 9, negative 6. Is there some number k that we could multiply A to B by, which is 1, 3, negative 2, so that they're equal? Pretty easy to see, right? K has to equal 3. So you do 1 exclamation mark, but then it looked like a factorial. that seems like a lot less work, right? So another strategy is showing things are parallel, and we haven't seen this, we haven't done a lot of work with parallel and lines yet, but if something is parallel with a vector, it's just some multiple of that previous vector, right? If I have the same direction, but I just make it longer or shorter, it will be parallel. So here we've easily shown that these 3 points have to be collinear. I like these ones. This is saying we've got points A to B, B to C, D, A, B, C, D, and E. And you can walk in these directions. What is it like doing in a more simple way? So this is what we have. We have A, B, C, D, E, A, B, C, D, E, and you can walk from A to B. You're allowed to walk from B to C. You're allowed to walk from D to E. And you're allowed to walk from C to D. Can you see that they all line up? And this is very much like starting here and ending here. So on the diagram, it works out really nicely to see that this answer is going to be A to E. In the mathematics, I might just start by, like, sometimes, I'm not going to draw out this diagram, by the way. Look at the second one. No. Don't want to draw out a diagram for all of that. But for the first one, I could go, oh, if I'm going from A to B and B to C, does it make sense that this one could be combined to be A to C? And then the order that you do these doesn't matter, but I'm now going to rewrite this, but I'm going to write the C to D and the D to E next. And then I might put these two together, because I'm like, ooh, these D's are the same. This is the same as going from C to E. And then I have A to C plus C to E. That's the same as going from A to E. So we can combine things slowly to get everything together. So this next one, it's just a matter of trying to figure out what you could combine and what you could put together. Right, we've got ACs and DCs, but the numbers in front, you have 4 of these and 2 of these. You could break this up, right, if you wanted to. So there's many options here, okay? So you could look at what letters could go together, what numbers there are. You could break things up. You could simplify things. Like, do you see that these two are the same, but one is positive and one is negative? Those two together, what would I end up with if I put them together? I would end up with 2 B8s. You don't have to do this first. Like I said, there's multiple options for doing this one. I'm just going to play around with, if you see something, we'll put it together. So I saw those 2. I'm going to rewrite everything else that I still have. Oh, I could do the same thing with these ones, right? Those two are the same, just in opposite directions. So I would still have 2 BAs plus 4 ACs. And those two, if I combine them together, would still be 4 CDs. Which ones?
DA, DA, DA.
2 BA.
Oh, no, no.
No? These ones though, do you see that these ones have the same mill number? So I could put those together, so now I've got 2 BAs plus, and 4 of these plus 4 of these will be 4. So it's also important that the numbers in front match up. Oh, and then now these are the same in different directions. So that would just be 2 ADs in the end. Oh, now those match up, and there's 2 of those and 2 of those. So all of that traveling, and you could have just got there so much quicker if you just started at B and went to D 2 times. And again, the order that we did this does not matter. We go back, like, I found ones that were the same that simplified. I wouldn't have had to do that. Maybe you wanted to do, like, let's see what would go together nicely here at the beginning.
The
There's-
DA and AC.
The DA and the AB. Yeah, you could do those two together right away. We could have started with this and got 2 DBs. Perfect. And then those 2 DBs might have fit with something else. Or you could have connected and broken this CD up into 4 CDs plus 2 CDs and combined those together. And whatever you choose, eventually it would have simplified down to the same thing, whichever way. So it's not like, oh, how am I going to remember the order that Mr. JR did this one if I have a question? Well, again, that's not the important part. The important part is just knowing that if you can put something together, go ahead, put it together, and then you can try. All right, we're going to leave the next question as a warm-up for next class.